Here is a short warning about set builder notation. So it is quite tempting to think that any condition defines a set. Like that you could just say, oh, the set of anything and that it'll work out, or the set of x's such that any property, right? And so we need to be careful about that. And this paradox essentially illustrates that. So let's consider the following set. So this is called Russell's paradox, and so Russell proposed the following set. Consider the set R, which is going to be all the objects, all the elements x, such that x is a set and x does not belong to itself, right? So it's supposed to be the set of all sets that do not contain themselves. And so now we ask, or I guess Russell asks a strange question. Does R contain itself, right? So let's see what happens. So let's first suppose R belongs to R, right? But then, by definition of R, it must be that, so because again, what is R? R is all the objects in R, they cannot be elements of themselves. Since R belongs to R, then R cannot belong to R. So in other words, if R belongs to R, then by definition, R cannot belong to R, and so this is a contradiction, right? So this cannot be true. It can't be that an element belongs and does not belong to the set, right? Okay, so suppose that the opposite is true. So suppose R does not belong to R. But then R satisfies the condition to be in R. Right? So, because again, R is all the sets where that set does not contain itself. So that set is not an element of itself, right? And so if R is not an element of itself, then it must belong to the set R. So thus, R must belong to R, and once again, contradiction. So in other words, if you define this set, and you ask yourself, well, like, can such a set exist? Well, then if R belongs to R, then it wouldn't. And if R does not belong to R, then it should belong to R. So you can't actually have a set like this, which means, so the whole point of the paradox is that it concludes, thus, this set, Russell's set R cannot exist. So this set cannot exist. And okay, this is quite a weird set, right? It's not the typical set that you might encounter on a day-to-day basis. But it does showcase something, which is that you need to be very careful when you define sets. You can't just go and define anything and assume that it'll work out. You need to be very careful, right? One way to avoid this is that if you do a construction, so if you do a construction of the form the x's belonging to some set S that you know already exists, such that some property holds, this will always be okay. So this will always exist as long as S exists. So you can always say something like the x's belonging to a set such that, and then any property you want. Notice that Russell's paradox doesn't have that form. It's not x's belonging to some restricted set such that something. Russell's paradox is essentially trying to talk about sets without saying where they are coming from in some sense. So that's one of the ways to avoid it. And so once again, the whole point here is, and let me write it out in red here. So the whole point of this video is that we must be careful. So we must be careful when we define, so defining sets.